time and sort of where the state of things are in the cloud and intrusion detection systems and what the next steps need to be. And again, I'm talking about OpenStack, so I'm talking about the open source world. Private companies are probably way beyond this, but you can't look at their code. Okay. So network intrusion detection systems, for a recap for those of you who are not familiar, what these bits of software do is analyze packets in real time as they arrive. And potentially can alert an administrator if something is detected that's malicious. And that action is sometimes called an active response. Network intrusion detection systems come in two flavors generally. There's what's called the so-called signature-based NIDS, and what those do is they have rule sets. And those rule sets are defined patterns to look for in packets. I'll have an example in a moment. And by and large, for the Snort, the example that I'm giving here, a canonical open source NIDS, these are maintained by the community. So there's a large number of people around the world. We heard about zero-day exploits a few minutes ago. They're very active, and almost immediately when a problem is discovered, it'll be added to these rule sets. There's another type of NIDS, which I won't be talking about, that is a little more complicated, and those are called anomaly-based NIDS. And what those do are, what they're capable of doing anyway, is looking at deviations from expected behavior. So they know what the normal traffic looks like. And if there's, say, a denial of service attack, which would probably be a big burst, that would be something that would be an anomaly. It would be unusual, and it could trigger on that. And it can do a lot more than that as well. So what these are is, instead of sort of fixed rules, which are a bit rigid, these are actually look like little programs which can detect, which you can do arbitrary work to look at network traffic. Here's an example of Snort rules. Each line there is a rule. Here, like at the very top one where it says SYN fin scan, well, it's looking for the SYN and FIN flags in a TCP packet. If a TCP packet arrives from any IP address to any IP address, any port to any port, or sorry, to HomeNet, actually, it's a destination, then it will trigger. Here's another example. Some of you in the security field probably heard of something called shell shocked, which was an exploit on the bash shell in Linux. It was a real bad one. It was a real scary one. The top rule there is what students in my class do. It turns out that you can detect bash by just looking for those 4 characters. And the bottom rule is the actual rule that Snort uses, which is a lot more robust. But this gives you an idea. So, onto the cloud. That's what an NIDS is. How are we going to get this working in the cloud? So there's 2 use cases that you would be concerned about here. And one is as a tenant administrator. This means that you are basically in charge of some number of instances. And that subset of the cloud that you manage is called a tenant. So you would want an NIDS to guard instances in your tenant. And basically, you would spin up another instance, an instance being a virtual machine, in the cloud, which would run an NIDS, and you'd be charged just like any other instance within your tenant. The key point here is that you do not necessarily have access to the guts of the computer that's running the cloud. You're a tenant administrator. The other one is you're the hypervisor administrator. In this case, you are the owner of the cloud. You have access to the hardware and can touch and feel it. And your use case here would be to have the NIDS guard every tenant and all instances on all tenants. So you would have to somehow uniquely identify instances. For those of you unfamiliar with the way clouds work, they might make it so that 2 IP addresses on 2 different tenants still on the same physical machine, might have the same IP address. That's something that can happen, the way it doles them out. So the way you distinguish tenants is something called a VLAN tag. Now I'm getting a little too technical maybe, but this is the sort of capability that is needed, and Snort understands VLAN tags. And you would also want different rules for different tenants. So those are some of the different use cases. Next, where would this NIDS go inside the cloud? So to talk to that problem, you have to look at what a cloud is. What does the cloud look like internally? So this is what OpenStack looks like internally, or at least the Red Hat distribution of OpenStack called RDO. It's made up of instances, which are the green circles. Each of those you could call your virtual machine, which are connected to and interconnected with a virtual network, entirely virtual almost. That's interconnected with using bridges, switches, software bridges. And that's what those blue rectangles are. So the blue rectangles interconnect the virtual machines. All right. Notice there's two types of bridges here that are important to bring your attention. One of them is the integration bridge, BR-int. That's the middle one on the lower left. That one connects everything to everything. It's sort of all instances go through there. So if you tap there, you can see all traffic from all instances. And then another one that's interesting is the one right above that, those little squares, QBR. Those are switches unique to each instance, and those are firewall bridges. They base it. So there's already in OpenStack, and I'm sure AWS is the same way, a unique firewall for each instance. And notice the instance itself can't have access to that firewall bridge. Okay. So how could you so given what we just saw, the plumbing of the internals of a cloud, where would you want to plug in a network intrusion detection system? Well, one idea would be in between that firewall that we just saw a moment ago and the instance. And so you could bring up another instance, another virtual machine, and that virtual machine would sit in between the external world and your instance, and basically sniff every packet and look for bad behavior. Well, I don't like that, and the reason is it's slow, though it would work. And I know people who are doing this in Red Hat, but it is a store and forward solution. So every packet that comes into that instance would have to be read in, analyzed, written out, and it would be slow. What you really want, and what administrators do in the physical world as opposed to the virtual world, is they put a tap normally, and the tap mirrors all traffic. So traffic that comes in is tapped, it's sniffed, and then shuttled off to a monitoring node, a computer that's devoted just to intrusion detection. But it's out of the way of the normal traffic. The normal traffic continues down to the instance. This way, traffic is not affected, or performance is not affected. The user doesn't know that the traffic is being sniffed and doesn't see any performance degradation. But you do need to allocate extra hardware resources for this. Or in the case of the cloud, the virtual machine needs to be allocated for this, which boils down to a core, a CPU core. That is being used for intrusion detection or administration rather than for your tenants, for your users. So it's overhead. So how would this be done? Well, what you want is a tap, which is attached to the integration bridge, and go to the network intrusion detection system. And this is what it looks like. Now, the next few slides here were for OpenStack people, and therefore I'm going to skip over them quickly. And furthermore, I just have 30 minutes. So really showing you all these funny little commands would just be a waste of time, because you're probably don't know what the words Nova mean, or neutron, or open virtual switch, or any of that stuff. I think the takeaway, though, with all this gobbledygook and all that plumbing, is that it's doable. You can do it. If you have OpenStack, you can get something called tap as a service, and you can implement something like this, which will effectively give you that, which is what you want. So this is a proof of concept here, which the details I think are not relevant for this talk, but it's there, and I could show you more after the talk if you want. Now, if you're an administrator, you have a choice. You can do it in your node. You have about, say, one big server where all your virtual machines are. Well, you could use that same virtual machine to run your IDS. You could do that. But you would be, as I said a moment ago, you'd be consuming one of your cores. Another option is to have a tunnel where you mirror the data off to another physical machine. You have another physical machine, which is, you need an extra piece of hardware for that. But that can be done using some more, let's call it what it is, gobbledygook. And that can go through what's called a GRE tunnel to the other machine. Yeah, this is more troubleshooting, again, for an OpenStack audience. Let's just go talk about performance for a minute here. Why would you care about performance with a network intrusion detection system? Let's say you did mirror the traffic. So it is mirrored, it's not affecting the user. But still, you have a limit on the physical machine on the number of cores you have, and that limit can be reached. What happens when it's reached? What happens is the network IDS won't be able to process them all, and they'll end up dropping them. So when that happens, it may drop a packet that should have been looked at, and now it wasn't. So you think things are okay when they're really not. And this problem is compounded because in the cloud, what you're probably doing is fanning in many, many, many instances to your one poor network IDS. So it's going to be very busy with all this traffic. Yeah. So if you're going to analyze the performance to see sort of what happens here, what happens in a cloud when you set this up, the components that you're interested in analyzing are those blue rectangles, the virtual switches, and how much CPU overhead the Snort, or whatever your network IDS takes. So you can look at those two things, and then you can figure out from there the feasibility of this. So first, talk about Open vSwitch. Now, Open vSwitch is the open source implementation of a software bridge which forms the plumbing of OpenStack. So it's a real key component. And you can get that software. It's like any other open source software, and you can get it and you can analyze it. And then you can look at how much work, what is the sort of upper bounds of this. And well, you can have up to 4K tenants. And you can configure, when you configure a cloud, OpenStack, how many instances per tenant you want. So you, as an administrator, know the sizing. So Open Virtual Switch performance is actually very good because it does most of its work in the kernel. It only has to go to user space. So this is a bridge. What does a bridge do? It maps Ethernet addresses to destination ports. And when I say ports, I mean the ports in the sense of that figure inside of OpenStack that I showed you earlier. So there's a giant table that maps these ports to Ethernet addresses, and that's called the CAM table. As long as that's in the kernel, it's very fast. If it goes to user space because it cannot find the Ethernet address that it's looking for in that table, then it's slow. But normally, it's all cached in the kernel. And there's no copies between interfaces. So like if you have one of those blue boxes and a packet comes in, it doesn't need to be copied to another port. It's just moving a pointer, I believe. And so that's really quick. But there's a problem when it starts to talk about intrusion detection systems, and that is, I think when you mirror traffic, it does copy it, unfortunately. And here's what happens when you copy that traffic. The number on the x-axis here is the number of mirrors taken. This is I give the citation below for where this came from. We would just be doing one level of mirroring, so we would be on, I think the number 2 down there, 2 output streams. But you can see the performance degraded by 30%. And if we were to mirror it again, it would be degraded further. So that's a problem with Open Virtual Switch. And so when I said the state of the world as things are now, that's simply a bug, probably, that could be fixed. I don't know if it's an architectural issue, and so I think that might be improved. What about the NIDS performance or Snort performance? Snort is single-threaded, which means it doesn't enjoy the benefits of multiple cores, necessarily. Some suggestions I've seen are to run multiple copies of Snort at the same time, but I don't know how good a solution that is. The new version of Snort that's coming out, 3.0, will be multi-threaded, and so should be able to use the multiple cores and should be better. It can also be configured with certain tweaks, say to use different algorithms to look for patterns in TCP packets. There's an alternative to Snort. It's not as well known, called Suricata. It is compatible with Snort. It is multi-threaded, and benchmarks have shown that it's faster. So this is an alternative that can be looked at. Or you can wait for Snort 3.0 to come out. As I said, this stuff's always changing. All right, let's talk briefly about HIDS, Host Intrusion Detection Systems. So what are host intrusion detection systems for? They're for searching for viruses. They're for checking the configuration on your machine if it matches your organization's policies. And it's for looking for tampered files. So if somebody's tampered a particular program to insert a backdoor, the hash of that program may have changed, and then you can detect that it has been modified. The open source HIDS that's most well known that I've come across is called OSSEC. And it's very nice because it can aggregate logs from multiple sources, and it knows how to parse logs from different sources. So Snort logs, var log messages logs, web application firewall logs, like you might be using for an Apache server. All of those logs can be read and aggregated and looked at in one place by OSSEC. And that's a central controller too. So you might have you might have hundreds of instances in your cloud, but one OSSEC manager could manage all of them. This is a horrible picture that looks like it's from 20 years ago. But if you were to imagine that these computers were instances, virtual machines, you can see that each virtual machine is piping data into one OSSEC server. And this is an interesting point too. OSSEC and Snort, they weren't meant for the cloud. These are systems that need to be upgraded to work in the cloud. So real briefly, file integrity checking is scanning for tampered files. You can choose what files you want to scan. So somebody might change bin ls to do something malicious. How would you know that? Well, you could have OSSEC calculate a hash on bin, all the files in /bin, and store them somewhere. And then periodically OSSEC will come back and it will look at each file in /bin, and if it sees a mismatch then it will know that something changed. So this is a time-consuming process. Having it work in real time is something I haven't seen. So there'd be a window between the time the change was made and the time that was detected, but that's a capability. Policy checking is while you have some configuration of your system that you require. For example, you might require that a file named etc.uml exists. It does exist. Or that SE Linux is enabled on your system. Secure Linux is enabled. Those are two rules, just to show that that's possible. Now, in OSSEC, when it finds something malicious happened, then it will generate an alert. That's an example alert when somebody tried to use the wrong password. That in turn can generate what's called an active response, which